Shall we start? Okay, so we were doing derivatives of trigonometric functions last time. So I'll just see whether you remember that. So tell me, what's the derivative of sine of x? What happened? Bolo. That is also okay, you don't need to, Very good. What's the derivative of cos of x? No, you tell.
Minus sine of x.
Okay. What's the derivative of tan of x?
Secant square x.
How do you know? We didn't derive it. So let's derive that. Okay, and also we will derive what is cot of x okay. So let's these we had done, and these we had done ab initio, meaning I had taken the function, taken the value of the function at x plus h, and then take the difference and divide by h and take the limit, right? These two were done that way. So let's do these using the rules of differentiation. So, okay, I don't like this. I forgot again how to do that. Shape. Good. Okay. Okay. Let's recall that if you have a constant times a function and you look at its derivative, okay, then it is c times the derivative. Okay, I'm just putting a prime to save some writing. And you remember what is f plus g prime, where instead of writing d over dx, I'm putting a prime. You remember that notation also. That is f prime plus g prime. Okay, and I'm more interested in this one right now. What is that?
F prime g
F prime g.
plus f g prime.
No.
It's like minus f g prime
Minus f g prime.
over g square.
Okay, so I'll use this last one to derive the derivative of tan x. Okay, so let's see. So d over dx of tan x is d over dx of sin x over cos x, right? Tan is the ratio of sin and cos. Okay, so now let's use this rule that if you have f over g, the derivative of that is the derivative of the numerator times the denominator minus numerator times the derivative of the denominator divided by square of the denominator. So that is derivative of sin x, which is cos x times the denominator g, that's cos x. So cos x times cos x is cos square x, and remember that cos square x means cos x whole squared. Okay, that's a standard notation, minus the numerator is sin x times the derivative of the denominator. Derivative of denominator is derivative of cos x, and derivative of cos x is minus sin x. So you get again a minus sin x, okay, that I have to multiply. So minus times minus is plus, and sin x times sin x is sin square x over denominator squared. So that's cos square x. Can you say something about the numerator? 1. That's 1. That's identically 1 for all values of x. So it is 1 over cos x, cos square x, which is same as 1 over cos of x whole square. Is that okay? That is secant x. Okay? Is that okay? 1 over cos x is sec x and sec x square or sec square x. Okay? So I will just write here. I think there is a way of, oh, it didn't work. So I go here. Nice. So this one is secant square x. Okay. Now I'll find out what is cot of x. That's also easy. So I'll do it. Okay, you can do it like d over dx of cos x over sin x, but I'll do it slightly differently. So I'll do it this way, d over dx of 1 over tan x, because cot is 1 over 10. Okay, you got the result? So let's check. So first a numerator. So derivative of the numerator, that is derivative of 1, which is 0. So 0 times the denominator, I don't care because it's going to give you 0, minus numerator times the derivative of denominator, which is derivative of tan x, which is secant square x. Oh my goodness. Divided by tan square x. Okay. How much is that? That is minus, this is 0, minus secant square x. Secant x is 1 over cos x. So secant square x is 1 over cos x whole square. Okay. That is the numerator part now. Now in the denominator, what do you have? Tan x square. But tan is what? Sine over cos. So sine over cos, that's tan. That's the tan in the denominator, right? So square of this. Okay, so you see cos x square and cos x square cancels. You have this minus sign here. Sin x square, 1 over sin x square is cosecant square x. Is that okay? So you also got that? So we go that here and supply it here. Alright. Minus cosecant square x. Is that okay? Okay, so that's about some of the simple trigonometric functions. What happened? Done? Good, very good. So, okay, let's move on to something else now. Not something else, but let's go back to our favorite thing, slopes and hills and valleys. Okay? So remember, to have a local minimum or a maximum or a local extremum, right? A minimum value or a maximum value is an extreme value. So that's why we call it local extremum or also relative extremum, relative to other points. When you say local, it's relative to other points. Okay? So first condition is that a point be a local maximum or a local minimum, or let's say be a local extremum, is that the first derivative should be 0, the slope should be 0. Okay? And then if it is a maximum, then the second derivative is negative. Cannot recall it. And the first, and the, if it is a maximum, then if it is a minimum, then the second derivative is positive. Okay, that's what we have seen. So let's take one example, a nice example. So f of x is equal to x cube. Okay? So that's the plot you can do, but we'll not plot it. We will first ask where are the extremum points. So what should I ask is for what value of x, let's call that value to be c. Okay? For what value of x, or for what value of, for what c, the first derivative is 0. Right? Please pay attention, you can play with that thing later. So what is the first derivative? F prime of x is, what's f prime of x? 3x square. So let's say I want this condition to be satisfied, so what should I write?
3x square is equal to 0.
No, I'm putting it this way.
F prime of c is equal to 0.
3c square is equal to 0. I'm calling it c, right? I'm saying the condition at points x equal to c. So that is, I should put f prime of c is equal to 3c square. It's equal to 0. So what is c? Okay, also just note that c is, this is a quadratic equation, but in general quadratic equations have two roots, but here both the roots are repeated, so you have only one, so both 0 and 0. Okay, so c equal to 0. Good. So now let's find out whether you have a maximum or a minimum at x equal to 0. Is that fine? That's what you want to know. So let's find out the second derivative. Why? Now what is f double prime of x? So take the derivative of this. This is 6x. So what is the second derivative at the point C? You want to know at the point C, right? So what's the second derivative point C? So what do we have? First derivative, slope is 0. Slope is 0. Do you have a maximum or a minimum? None. None of those conditions are satisfied. So let's see what it looks like. Okay? So let's plot x cube. Okay, let's plot x cube. I don't like that color. Is it possible to get, nice. Let's see. Okay. Okay. So that's x and that is x cube. This is, so I mean I can put the values 1, 2, 3 here and other things and then plot, but I will just give you some idea what it looks like. Okay. So x cube, when x is positive, x cube is positive. So when I am plotting for these values of x, it will be in this side. When x is negative, then x cube is negative. So here it will be in this side. So it will be filling up this region. Okay. Now the derivative is 0 at x equal to 0. The derivative is 0 at x equal to 0. Okay. So it will be like this. And also you see f of x keeps increasing look at the slope. The slope is always positive, right? When x is positive, the slope is always positive. So it is always positive. And the slope is increasing as you increase the values of x. So the function will look like this. And I ask you to get a proper curve by taking few values of x, mark it on the graph paper and draw it. Okay, so you see the slope is here 0. And now we go to the negative values. So again the slope for negative values of x is what? Is it negative?
Slope.
Yeah, look at the slope.
Slope is positive.
Slope is still positive. See here the slope is like what? 0, positive, 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 positive. So here also. So here should be like this.
Yes.
Right? Positive, positive. But here it should become 0. So it should start tapering off. So positive, positive. So it is like this. You should check that it is like this. It's fine. Don't look at that side. If you don't look like it, don't look at it. Happy now? Okay, so you see, just because the derivative is 0 doesn't mean you will have a maximum or a minimum. You may have this guy coming to 0, slope becoming 0, but instead of turning or coming this way and slope becoming 0 and turning upwards, the graph may just become horizontal and then go that way. Okay, this is called a point of inflection. Oh my goodness. Is this correct spelling? Inflection. Inflection, okay. I'm comfortable being wrong, so no problem. Is that okay? So that's something that can happen. Now, maybe I should. Okay, maybe I'll not tell you. Or maybe I should just see here. Look at this. First derivative is 0 at x equal to 0. Second derivative is also 0 at x equal to 0. And then you see you get this. But then what if third derivative is 0? And the fourth derivative is not? What if all the derivatives up to 4 derivatives are 0 and the fifth one is not? So I will leave it to you to think about it, and the best way will be for you take graph x cube, x5, x4, x5, x6. You can plot them using graph paper, or you just use some tool or go online and just say graph of x to the 4, graph of x to the 5, you'll get it, and then look at it, okay, and see if you can understand a pattern from there. Now before closing this part, I want to give some, tell you about some notation and some names, okay? So that you can easily refer to those things. Okay. So as I said, maximum and minimum values are also called extreme values. Okay, not surprising, that's a reasonable name. And local, why this? Oh, with, okay, I understand. So I can directly go to another color with this, right? Oh yes, I forgot it. Now, if you have a local minimum or a local maximum, See, this one is not referring just to local minimum or local maximum. It could be a global. Did I tell this thing? Okay. So local minimum or local maximum are also called relative extrema. Okay. So extremum is singular, extrema is plural. Okay. So relative. You understand why relative? Because when you say local, you are comparing with what is happening in the neighborhood. So it's relative to that. So relative extrema. So it's a relative extremum at that point. Maximum, right? Relative extremum. That's the plural thing. Okay. So if a function in a region, in an interval, region is not good, interval, we are looking at functions of single variable x. In an interval, if it keeps increasing or keeps decreasing, then you say it's a monotonic function. Monotonic. Did I tell this also? Okay. You know tone, besura. Besura, one who does not have. Okay. So if the function is not changing, it's not becoming, no, it keeps growing and then comes down, then it is not monotonic. So monotonic functions. Monotonic or monotonic, I don't know, functions. Okay. So let's look at this. In this region, from here to there, you see this function is continuously increasing. So it is a monotonic function. Okay, we say it is monotonically increasing. And if you have a function like this, then you see as x increases, the function value is going down, and it is always going down, so it is monotonically decreasing. It's a monotonically decreasing function. Is that okay? Now let's look at another function. And how do I look at that one? So I will, where is the color? Can I just go here and change it to green? Okay, let's look at this one. Horrible. So here, green. Yeah, I selected green now. Now look at this. In this interval from here to there, here to here, from here to here, this function is not monotonic because it is here up to this range, it is up to this point it is monotonically increasing, but then it starts decreasing. So it is not monotonic. Okay. Okay, so this is this. One final thing, I'll just write it down. I'll write it down here. So a point C you're not able to see? Is that okay? A point C at which either the slope is 0, okay, or f prime does not exist. okay, it doesn't exist, is called a critical point. Okay? So when you are asking for local extremum, you are going to first going to try to find out the critical points, say where the derivative is 0. Okay? But critical point is also referred to those points where the derivative does not exist.
Kink.
Very good. It could be a kink, it could be something else also.
Infinite.
Very good. So you could have a function which is, so let's say function is like this. So the function is going to infinity and the derivative is not defined, okay? Or you could have just simply a kink. So a function could be like this. So here you have a kink, the derivative does not exist. Very good. Excellent. Okay, let's stop this video here. I will start something new in the next video.